Our next talk is from Mehdi Sadaghar from KU Leuven about unlinkable privacy compliant signatures.
Yeah, thank you so much for the introduction. So this is a joint work with Christian Weidercher from Input Outputs and Henry Coleman from the University of Maryland. So I'm pretty sure that most of the people in this room are aware of the digital signatures. So digital signatures are somehow necessary to bind a message to its author. Okay? It provides us authentication, integrity, and non-repudiation. So there are many examples and applications for this type of cryptographical primitives. However, in this talk, we only focus on financial transaction applications, and more importantly, in the cryptocurrencies. So let's quickly summarize that what is happening exactly during the transaction, okay, in the UTXO cryptocurrencies. So Jasmine and Aladdin are going to create a wallet, and they will receive a key pair, secret key, and public key. So whenever Aladdin is going to, Jasmine is going to send $5 to Aladdin, it gets the public key of Aladdin, and then sign the transaction details, the amount of the transaction, and also the recipient ID, and then send it to a group of the validators that we know them as the miners, okay? And the miner check the validity of the signature and then make sure if the signature was created correctly by Jasmine in this example. It's not only about the checking the validity of the signature, it's also about checking the balance of the Jasmine, okay? Jasmine might send $100, but she only has $10 in her account. So we have like somehow a transparent fish tank in this scenario, that the balance of everybody in this setting is visible to everyone. So in this scenario and this example, Jasmine right now has $10. She wants to send $5 to Aladdin, and after finalizing this transaction, Aladdin will receive $5 extra and will be top up in his account, okay? Needless to say that having this fish tank and transparent fish tank reveal a lot of information, including who is the payee, who is the payer, and so on. However, it's the pseudonym, it's not the real ID. I talked about Aladdin, but there are a lot of research that somehow link the pseudonym to the real ID of the user in the cryptocurrencies. If your employer sends, your salary in Bitcoin, then anybody can see that how much you are receiving. If you are living in Europe, it's not a big deal, but if you are living in US, this might actually be sensitive information. So this is the main motivation behind DApp, is decentralized anonymous payment systems like Zcash, Monero, Tornado Cash, and so on. The identity of the involved parties, including and also the transaction amount, will be hidden in this scenario. It's very important whenever you are making a private cryptocurrency or any other application, it's a very good framework, a place for illicit activities. Money laundering, tax invasion, and so on that you can see in this slide. So the main research question in this paper is how we can find a good balance. So we know that the regulators are looking to avoid such illicit activities in the system. However, the users and service providers are looking for having a good privacy, okay? So we are actually trying to find out what is and how we can solve somehow a dilemma here. There are also some solutions like accountable privacy. Like if you are sending this transaction using Zcash and Monero and everything is hidden, you can also encrypt the transaction detail, and there are some group of auditors that they can open up. But it's not a good solution, definitely. If there is everything hidden, how the auditor can be suspicious to a transaction if they are not going through brute force? And additionally, prevention is better than the cure, okay? So all of these solutions are saying that, okay, the transaction can happen and afterwards I can open up and see who was involved. But we are looking for the prevention in this mechanism. If this is illicit, then it's not going to be finalized. We also have in the real world, it's some substances or some items are limited to some specific buyers only, okay? It's not easy for any random person to go to a shop and buy some radioactive substances, for example. But if you are working on a research lab or some university and you are working for the research purposes, you might actually receive a certificate for this purpose and they can actually buy you this. I want to highlight the importance of the joint policy in this scenario, in this example, okay? So we are not only talking about the person who wants to go and buy this item, we also want to talk about the feature and the attributes of the shop as well. I mean, this person does not have any restriction for going to the grocery shop for buying other items. So let's again back to the previous example that we had and how we can bring some cryptographical solutions. Maybe there are some other solutions, I'm not aware of it. But we are looking for some cryptographical solutions to bring this policy during the transaction validation. So we already talked about that Jasmine and Aladdin are owning a key pair of secret and public keys. And now imagine that we have a policy, we go to the regulator, please give me your policy. If you are concerned about some actions, for example, tax evasion and so on, just provide me those policies, and now we have a setup in the system. Okay, it's different from the permissionless blockchain like Bitcoin and Ethereum that we know, but in this scenario we have a setup for the users. Again, the users receive a key pair, the secret key and public key, and also, we want to, as we already talked about, we want to actually have a policy to decide about the validity of the signature as well. So these two properties are necessary in this research. Additionally, we would like to have a joint policy. And also, whenever we are talking about the attributes of the users, during each of these transactions, there shouldn't be any leakage about the involved parties. Okay? And also, imagine that I'm going to send another transaction. There shouldn't be any link between my transactions. This is important also for the privacy purposes. So we are looking for these 5 features and properties in this paper. If you are working on cryptography, you might actually notice some of these features already that are similar in some other cryptographical primitives as well. Like in the digital signature we talked about, it's just about unforgeability of the signature. It doesn't provide any of other features that we are looking for. The closest construction and primitive is policy compliant signature from TCC 21, but the problem is that construction does not fulfill the unlinkability feature, and you can actually track the users based on their transaction in the system. In the unlinkable policy compliant signature, which is one of the contributions of this paper, we have 4 entities. Jasmine, the same, who is the sender. We have Genie, who is the trusted third party in the system that we want to actually issue the secret key for us. We have Sultan, who is the verifier in this scenario. You can think of the verifiers or the miners. And also we have Aladdin, the same actor. We have 5 algorithms instead of 3 that is more common during the digital signature: setup, keygen, rank key, and signing and verify. Let's arrange them in this way. So during the setup phase, Genie gets the policy as an input and generate the master public key and master secret keys. Using the master secret key, it gets the list of the attributes of the involved party who wants to join to the system, and then generate a key pair again, as we already discussed. Both of these parties, not in this image, I mean this slide, can actually publicly, without being reliable on the Genie side, can re-randomize their key to make completely unlinkable the process without having any limits. And during the signing phase, the Jasmine who wants to sign the message now gets the most recent updated version of the public key of the Aladdin, and then used her secret key to sign the message, and essentially Sultan can decide based on the most recent updated version of the public keys. More importantly, I have to emphasize here that Sultan as a verifier is not going to check a checklist to see that whether the attributes are actually involved in this transaction or in this signature or not. So the ingredients that we are using are zero knowledge proof system, digital signatures, predicate encryptions, and also pseudo-random functions. And also for the instantiation, because we have a very detailed proof of concept as well, we have 3 proposals for making these systems possible. And for the digital signatures, we are based on these constructions. I don't want to read them because of lack of time. And also for the predicate encryptions, we are using the OT12 predicate encryption, and pseudo-random function, we are based on the Doodle-Swampscopy fairness construction. And for non-interactive zero-knowledge proof systems, we are using 3 different zero-knowledge proof systems: bulletproof, which is a range-proof, Roth-Sahel proof systems, and also we are based on Schnorr. So some of you might actually be worried about, okay, it's very fancy, it's very beautiful to have such a system. How efficient is this? Okay, it's not efficient at all. But I have to emphasize that, so it's like a proof of concept. It's not a full-fledged deployment that somebody can use it. But if you check the 10 attributes for a user, you can see that the signing process is around 5 seconds. And for the verification of this signature, you also need to check that 5 seconds. So it's not good, okay, definitely. But there are some space to actually make it better, definitely, if you are interested to work in this line of research. It's just a proof of concept. We also have two other alternatives. We actually implemented the first one. We call it generic construction based on the inner product relations. But we have two other policy logic as well. One is the role-based and another one is separable policy that we achieve the constant overhead in most of the cases. So this is the result that actually I talked here. And this is the detail that we actually included in the paper. I totally recommend everyone, if you are interested, please take a look to the paper. What we didn't discuss is the security properties of these systems. We care about the correctness, unforgeability, attribute ID, and unlinkability. We define them, and we also prove them formally. Additionally, we didn't talk about the detail of those other primitive, the alternatives that we talked about. Also, we have a detailed zero-knowledge instantiation in the paper that you can check, and also some other applications. Very quickly, I just want to mention some potential future work, minimize the trust that we are actually relied on the central entity, and also design a better predicate encryption that makes the system more efficient, and also design the same concept and achieve the same property, however, with different techniques. This is my talk. Thank you. Any questions?
Any questions for the author?
You need a mic or you need to go on?
Huh?
There's an online question.
Is there an online question?
Yes.
Please go ahead.
Go ahead with mic.
Can you hear me?
Yeah, he's
Yes.
Yes.
Oh, great. Okay. So, in financial systems like this, the policies generally can't be written as a computable predicate, right? Like the intent of the transaction is part of what makes it legal or not legal, right? So, where do you even start if your predicate isn't can't be decided just by looking at the content of the transaction?
So yeah, that's true. That it's not that much easy to actually bring the regulation. Imagine that you want to bring the GDPR that computer understand. Okay, the people even don't understand, and it's really hard to actually bring all of this stuff to the mathematical facts, because we are talking about inner product equations, for example. So actually, I'm not sure if I understand correctly that how we can actually bring the policy to the transaction level. If something is happening on the blockchain is immutable, okay, so we cannot alter it later and bring it back to the previous state. We just want to prevent it because of the integrity and authenticity of the digital signatures.
Right, but when you're deciding whether to allow a given transaction or not because it's money laundering or something like that, you can't tell if a transaction is money laundering just by looking at the transaction.
Definitely, that's a very good point, but I need to emphasize, there might be some metrics about this, okay? It's not easy, it's not trivial as a researcher, as a cryptographer, that how we can actually transit from the existing concerns in the financial systems to the mathematical fact and cryptographical solutions. But now think about, we can actually define, I'm showing a slide right now, it was a backup slide, that we can actually design some metrics about it. We already talked about the attribute-based credentials. It's very similar concept. The nationality, the age, and some other concerns can come to rescue, but it's not, I completely agree with you that it's not that much general concept to avoid and understand that it's a tax evasion or some other aspect that we already discussed.
Do you have a further follow-up comment, or?
No, that's fine. Thank you.
Maybe the author can take the rest of the questions offline. We'll invite the next author, next speaker.